Okay, this is an example where I have a infinitely long cylinder with a uniform magnetization, and I'm asked to find the magnetic field everywhere for this situation. In this case, I'm going to actually do it first by using the definition of the bound currents to find the bound current in this situation. Then I'm going to use the bound current to find the magnetic field, because the magnetic field is always given by the full current. The magnetic field B is always given by the full current. And so the definition of bound currents, right, my bound volume currents is going to be del cross the magnetization vector M. If I have a uniform magnetization vector, of course, this is going to be 0. And then the surface current, K, is N hat. M cross N hat. In this case, N hat is going to be in the S hat direction, and M is in the Z hat direction. So this is M naught in the Z hat cross S hat. Z hat cross S hat is going into the page. Into the page is in the positive phi hat direction. And so this says that my bound surface current is M naught phi hat. And so I have a current that is on the surface going in that direction. Now step 2 is to find the magnetic field everywhere. To find the magnetic field everywhere, I'm going to use the Ampere's law, because I have a symmetric system here. This is essentially an infinite solenoid. And so the two loops that I look at in this case, right, is ideally I look at a loop where one of the radius is at A and the other radius is at B, and we make the assumption that B is much, much farther away than A. And then the next loop we look at has, again, the inner radius at A and the outer radius at B, but now the inner radius is interior to the loop and the outer radius is exterior, as opposed to both interior and exterior there. One of the things that we're going to make, one of the statements that we're going to make here is due to symmetry. I know that my magnetic field, B, should depend only on my distance out from the center, and so it should only be a function of S, and it should only point, in this case, in the Z hat direction. Z hat. Going and looking at Ampere's law says that the integral dl dot B is equal to the mu naught times the current enclosed. Well, on these two integrals, first of all, for this first one, so let's call this loop 1. For loop 1, the current enclosed is 0, and we have this B is in the Z hat direction. dl here we can make is going to be either in the Z hat or the S hat direction. S hat dot Z hat is 0, so the only two contributions will come from these parts. If we say that the size of this loop, this square loop, is L, or the size of this rectangular loop is L in the Z direction, from this part we're going to get L BZ at B minus L BZ at A must equal 0. Now, the statement that we're going to make is we believe in the limit as B goes to infinity that this term here must go to 0. But this is true no matter where we put B, so this means that BZ at A must also equal 0. Okay? And so we have BZ at S must equal 0 for S greater than the radius of our object here. Okay, let's call it R, greater than R. Now for the second loop, we are going to have a very similar expression. We're going to have Okay. In this case, the way I've drawn this is the n hat, okay, is pointing out of the board for this guy. And so that's in the minus phi hat direction. So now I'm going to get L times BZ of B, which we know is 0 because of that statement, minus L times BZ of A. Now this is going to be equal to the mu naught times the enclosed current. Well, what is the enclosed current? The current is flowing opposite the direction of the unit vector on the surface. The unit vector on the surface is coming out of the page. The current is flowing into it. And so we're going to get a minus sign, so that's going to give a minus. And then it's just going to be the surface current times this length here, which is L. So this is K times L. This is going to be, in the end, that minus L BZ function of A is equal, plugging in for K we found is m naught, minus mu naught L m naught. L's cancel, minuses cancel, and it says that the BZ as a function of A is simply equal to mu naught m naught. And so we find that BZ, so we find that the magnetic field is going to be mu naught m naught in the z hat direction, as long as s is less than the radius, and 0 if s is greater than the radius. There we go. That's how we can solve this problem.